All right, hello everyone. Welcome to chemistry midterm review. Um, as some of you know, I originally was going to have a Q&A session that also went over the midterm, but I just couldn't find the time, but I have some right now, so I wanted to take advantage of it. So just as a reminder, the midterm will begin at 6 p.m. on Monday, and it'll be due by 10 p.m. on Monday. You'll be able to download it same day. So anyways, let's go over the logistics here. So some themes you're going to find on this exam will include the scientific method, the basic stoichiometry, basic introductory knowledge about atoms, protons, neutrons, electrons, their charges, oxidation numbers, the periodic chart, things like that. So let's start off with the scientific method, right? So the scientific method is obviously the method of which we do science, right? And so I just have a couple of brief things to go over about it. The first thing you're going to do in the scientific method is you're going to ask a question, and sometimes this is referred to as selecting a problem. From there, you're going to hypothesize what it is that might solve this problem. And a hypothesis is an educated guess. It is referred to as not quite the solution to a problem, but a proposed solution to a problem. And from there, well, you need to test your hypothesis with an experiment. And you need to either prove your hypothesis right or wrong. Now, from your experiment, either during or right after, you're going to gather data. And then once you analyze that data, you're going to come to a conclusion. Now, the scientific method is not finite. It doesn't have, or linear, I should say. It's not linear. It doesn't always have to go this way. For example, you selected a problem, you came up with an idea to solve it, you experimented, and it didn't work. So you come up with a different hypothesis and experiment on that until you eventually get to a conclusion. Now, all the times that you've proposed a new hypothesis should be included in there. So side deal. So scientists use the scientific method as a way of thinking and not just a way to do experiments. We do this, we do this because it's the same around the world, and this is obviously worked out. And also, I wrote here, results data is also referred to as the results section. And what's important to know about this is that this is going to be definitive. This is not your opinion of what happened. This is what happened. This is the facts of the experiment. Same thing with your hypothesis, believe it or not. Although it is your idea or your educated guess, it's a definitive statement. You don't say, I believe, or I guess, or I think. You say, a definitive statement. So that is the scientific method in a nutshell. And, this is a chemistry class, so don't expect too many questions about the method itself. Now I'd like to go over, make sure I'm still in view here, the process of scientific notation. And I'm going to go back and forth. So meaning from scientific to standard and standard to scientific. So let's take a small number such as 0.0089, and that's it. Okay, not that small of a number, but a pretty small number indeed. In science, we don't really like to use these numbers necessarily. Instead, we're going to use scientific notation. So what we're going to do is we're going to take this number here, and we're going to include it in our main number. And it'll look like this. To turn this back into scientific notation, what you'll do is you'll find the first whole number, and you're going to put a decimal right after it. Okay. So now you see we have 8.9, right? 8.9. And then you ask yourself, okay, how did I get there? Well, you move, let's see, 1, to 3 spots to the right. So that's going to become important in a little bit. So first of all, we obviously are 8.9 times 10 to the, and we moved 1, 2, 3 spots to the right. So we're going to put -3. -3. Now let's test this. Let's see if we actually did it correctly. So to go back to this original one, we're going to take this number and go back. So we have 8.9 times 10 to the -3rd. This means that I'm going to move the decimal this way when it's negative. So we're going to take 8.9 and go 1, 2, 3. We're going to fill these in with zeros. And that decimal has landed right here. And that surely gives us that, which is, of course, what we had up here. So that's one example. But let's go a different direction. Let's say we have this number here. It's kind of a big number, right? And maybe we don't want to say 15 million. Maybe you want to put it in scientific notation. So what you would do is obviously you would identify where the decimal is. Well, the decimal is here, 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 here. If you can't find the decimal in a whole number, it's always to the furthest right, okay? And that makes sense because if the decimal was here, then it wouldn't be 15 million anymore. If the decimal was here, it would be 1.5 and so on. So we always know the decimal is the furthest to the right in whole numbers like this. So we're going to do the same procedure as we did before, but we're working in the opposite direction. So we're going to find that first whole number, which would be 1 in this case, and we're going to put the decimal after it. Okay, so I'm going to write 1.5. And now we're going to work this way. I move the decimal 1, 2, 3, 4, 5, 6, 7 times to the left. So I'm going to write times 10 to the 7th power. So an easy way to remember this would be that big numbers like 15 million here, they will have a positive exponent. Small numbers like this number here will have a negative exponent. So if you can remember that, then you should be good to go. Now let's turn this back into 15 million. All right, so we got 1.5. And I'm going to move the decimal to the right 7 times. 1, 2, 3, 4, 5, 6, 7. And I'm going to take all of these, add in my zeros. And sure enough, I got myself 15 million. There you go. So those are examples with small numbers and big numbers. And please remember, small numbers get a small exponent, negatives. They get negative exponents. Big numbers get positive exponents. That's one way to remember it. Now, which direction do you go? How do you know which direction to move the decimal? Okay, so in this case, obviously in this scenario here, we went 3 to the right because we had to. You're not going to go left. You're going to go right. 1, 2, 3 to the right. And when you go right, it's negative. When you go left, like we did here, went this direction, it's positive. So that's another way to remember it. If you like the small numbers get negatives and big numbers get positives, remember that. But if you want more, technical, fine. If we move to the right, it's negative. If we move to the left, it's positive. Now that means if we were to start in scientific notation, for example, if I put 1.68 times 10 to the 5th power, well, what are you going to do with that? When it's a whole number, it's big, right? So I am purposely going to make a mistake so that you don't make it on the test. If I wrote 1.68 and I was like, okay, I'm going to go back 1, 2, 3, 4, 5, fill all of these in with zeros. This is the wrong answer, to be absolutely clear. And I was like, okay, that's my final answer. That doesn't make any sense because big numbers get negative integers, not positive, or integers, exponents. not positives like this. So I know this is wrong because this is positive. So keep that in mind. The answer is this. It's the 1.68. And then I'm going to move the decimal 5 times to the right. 1, 2, 3, 4, 5. And you fill those in with zeros. And my answer is 168,000. That's 168,000. That's the final correct answer. Let's do another one of those. So in this scenario, I'm going to have 5.2 times 10 to the negative 2 power. So we know it's negative, so it's small. So I'm going to do this. 5.2, we're going to go 1, 2 to the left. Fill that in with a 0, and then we get 0.052. And that is the correct answer. So in this exam, I don't have any fill in the blanks. You'll be able to pick among 4 or 5 options as to which is the answer. And you better believe that I put both of these answers on there, whether you did it right or wrong. So you have to keep these rules in mind. So small numbers get negatives, big numbers get positives, and that should help you enough. So that's scientific notation. It's not just it's not going to be only for this exam. It's going to be for a lot of things, and it's really useful to write big numbers. So make sure you understand it. And let me go back to my thing here. Okay, so now we're going to go over different types of changes, physical versus chemical changes here. So first of all, let's just take this piece of paper. I have it upside down on purpose. Let's take this piece of paper. It's made out of mostly carbon molecules, and I know that because it was once alive. This was once a tree, so it's mostly carbon molecules. If I were to just rip the paper here, right? It's still paper, right? I can still write on it. It does its job. This is a physical change that just happened. I just changed the size of the paper, but it's still paper. I can still write on it. When we have the addition of chemicals, let's say isopropyl alcohol, to other chemicals, then you will see a color change and a change in its properties, its chemical properties. So this isopropyl alcohol just made this paper see-through, because now you can see the other side of our paper here. This is a chemical change. All right. If you notice a change in color, and I notice a change in odor as well, that's a chemical change. This up here was a physical change. Why? Because it's still paper. It's still going to do paper stuff. This is not paper anymore. I don't know what it is. I don't know what you call it. But the other side even looks different as well. And I'm not even going to try. I can't even write on it anymore because it doesn't do its job. So when it changes properties, changes color, changes odor, changes other chemical properties, changes its chemistry, I should say, it's a chemical change. When it changes its size, its shape, it's physical. So an example being the paper that I just ripped off earlier. If I take it and I fold it, as many times as I want, it's still paper, right? This is a physical change, but then if I were to pour it in the isopropyl alcohol, then it becomes something different, and it's no longer paper, therefore it's a chemical change. Really common example that you'll see would be water, right? So if we have our little beaker of water and it's got flame underneath it, obviously pardon my drawing here. So we have water in here, and you know what happens, right? When water starts to boil, it starts to release this gas. So my question to you is this a physical or a chemical change? Specifically the gas right here. Well, you might be surprised to learn that this is a physical change and not a chemical change. Why? Because all of these water molecules are the exact same thing as what was in the beaker. Nothing has changed about them other than their size. Just like the paper, right? Paper changes size, therefore it's physical. Now, if I were to add some sodium chloride to the mix, then yes, it is a chemical change at that point because I've added a new chemical in there. Hopefully that makes sense. What is the next thing on my list? Oh, you know, actually, I can actually talk about that. So this is a saltwater mixture, right? You got salt and water here. This would be considered to be homogeneous, right? Because in reality, you would not be able to pick out the differences between sodium chloride and water. You couldn't do that. You could separate them using heat as in this example, but it's different. In a heterogeneous mixture, you'll have things like a salad, right? You've got your lettuce and your cucumbers and more lettuce and tomatoes, and you can pick out what you want, right? I want the lettuce, I want the cucumber, I want whatever this is. And yeah. So in homogeneous, you cannot pick out what you want, at least physically. But in heterogeneous, you can. So think of like a salad or like a chocolate chip cookie where you can pick it out. That would be heterogeneous. Homogeneous would be like milk. You can't do that with milk. And in addition to this paper, those elements that I named, or rather compounds, NaCl and CO2, these are considered to be compounds because they contain one, two, or different types of elements. Now, if I were to separate those two things, you got sodium, and then chlorine, and hydrogen, and oxygen. These would all be considered elements and not compounds in their individual cells. So elements make up compounds. And then when you mix a bunch of compounds together, you can get a mixture like this. So in the grand scheme of things, we go from very small to mixing them up and making a little bit bigger, and then getting very big, and then it just depends on how you mix them from there. So hopefully that answers that. Now inside the atom itself, I'm going to draw a very rudimentary atom here. So that's the nucleus. That's one electron ring. That's the second electron ring. That's the third. Remember, electrons orbit the nucleus. So I'm just going to put them. Remember, E negative means electron. Inside the nucleus, we have protons and we have neutrons. So I like to write mine in shorthand. I like to write protons as P plus, neutrons as N0, and of course, electrons as E negative. Because that'll force me to recognize their charges. But where are they placed? So neutrons and protons are in the nucleus. They never leave the nucleus. They stay there forever and always, unless we're talking about nuclear chemistry, in which case that guy goes somewhere. Electrons orbits the nucleus. They never go inside the nucleus. They don't need to. There's no need for them to do that. Now the electrons specifically out here on the outermost level, on the outermost shell, we refer to those as valence electrons. And those refer to electrons that are on the outermost shell. Now, why are these important? Well, these guys are going to be in charge of actually bonding themselves to other atoms. So not these guys, not these guys, but these guys right here. They are going to be in charge of doing that. Now, when let me go to the next part here, just to make sure I have. Very good, okay. So without getting too far ahead of myself, the rule for valence electrons is called the octet rule. And it's an important rule to know because it pretty much dictates what will bond with what, at least ionically. So Octet, obviously the prefix oct means 8. But 8 what? We're talking about 8 valence electrons. So if you get to 8, you're happy, you're good, you're satisfied. But anything below 8, you're not happy anymore. And that'll come into play later when we start talking about chemical bonding. But for right now, let's talk about the periodic table. So I have my periodic chart, but I'm just going to show you a bigger example for right now. So on your periodic chart, you'll get individual boxes. And for example, in this case, I'm going to put hydrogen. It's the easiest one to remember. Okay, that's what you're going to see for each element. This is called the atomic number. This is, of course, the atomic symbol that you're going to need to know. And this is the atomic mass. So the atomic number is really useful, especially if you don't like math. So atomic number tells us two things. It tells us protons and electrons. How many of them there are, how many protons and electrons are in there. So in hydrogen, theoretically, there's 1 proton and 1 electron. 1 proton, 1 electron. No math involved there. If you can see a number, that's it right there. Now the atomic mass is a little bit different. That is the sum of protons and neutrons. So when you add protons and neutrons together, you get the atomic mass. So finding protons and electrons is easy, right? You just look at the top number and boom, you got your answer. But how do you find neutrons? Well, you take the atomic mass and you subtract the atomic number. Atomic mass minus atomic number equals neutrons. If that is too complicated, I have another way. You could also say bottom minus top. Right? Because the atomic mass is the bottom number, atomic number is the top number. So you could also say bottom minus top will also get you neutrons. Either way is acceptable. I don't have a preference which one. But anyways, so yeah, this tells you protons and electron count. This tells you the symbol, which is important. And this tells you the sum of protons and neutrons in the nucleus. And then when you subtract these two, bottom minus top, you get the amount of neutrons. So therefore, in hydrogen, we have 1 proton, 1 electron. But then when we figure out neutrons, 1 minus 1 is 0. So there's 0 neutrons in hydrogen. But in other cases, of course, you're going to have more. Hydrogen is the only one without a neutron, so everything else does. Sometimes they'll be equal to the proton count, sometimes they won't, especially as you get down to the 3rd row there. So that's how you figure out all of those details. It's a good idea to practice with that. But now I want to start talking about the periodic chart itself. So, as all of you hopefully remember and know, this is the periodic chart. I want to be clear, yes, you can use this on your exam, even if you wrote on it. It's fine with me. I have no problem with that whatsoever. So first of all, let's talk about its orientation. So we have rows that go left to right, and we have columns, sometimes called groups, sometimes called families, but we have columns, groups, and families that go up and down, right? This whole thing here. And of course, on the top here, we have the numbers of those columns, and then what got cut off in my printer is the numbers that are supposed to be on the sides there. But this is row 1, row 2, row 3, row 4, and so on. So talking about going back to valence electrons, remember valence electrons is the electrons in the outermost shell. We got one valence electron in column 1 because it's in column 1, 2 valence electrons for column 2. We have to skip all of these columns right here, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, to get to 13. There are 3 for column 13, 4 for column 14, 5, column 15, 6, column 16, 7, column 17, and then 8 for column 18. So I told you earlier the octet rule, right? The octet rule is that all elements want to have 8 valence electrons. And elements tend to be all or nothing beings. They like to either have all 8 or none at all. And that's how they live. So all of these guys are happy because they have 8 valence electrons. They don't want to be like these guys who are always trying to be like them. This is the cool kids table. Everybody on this chart wants to be in the cool kids table because they have 8 valence electrons. So they're going to do various things to get to this status here. And give you an example, right? We'll take beryllium. Beryllium has an atomic, beryllium has a valence electron count of 2 because it's in column 2. Now one day, beryllium decides to have a party, right? Invites 8 valence electrons in total because he wants 8, but instead only 2 show up. Now, if you invited 8 friends to your party and only 2 showed up, you would probably get rid of those 2 people. You may or may not, but elements, remember, they are all or nothing creatures, so they will get rid of those 2 people. Now, those 2 people are wandering the streets looking for a good time, and now here comes oxygen. Now, oxygen's on the other end here. Oxygen's got 6, invited 8 people, 6 of them showed up. Not bad. Oxygen just needs 2 more people to come to his party, and he will be the cool kid. Well, beryllium just got rid of 2 people. Now, oxygen's going to take those 2 people. And as a result, oxygen is very thankful to beryllium, and they will now become friends. And in chemical terms, they become bonded. Right? We get beryllium oxide. Beryllium oxide. Let's do one more of those. We have potassium. And we have fluorine. So potassium has 1 valence electron, fluorine has 7. So fluorine only needs 1 more to get to the cool kid status here, and potassium doesn't even want his only friend that showed up. So potassium is going to get rid of its only friend and transfer it to fluorine, who now has 8, and they bond together over this. So we get potassium fluoride out of that. Now, what I'm doing, I'm going from one end of the chart to the other. That's called an ionic bond, right? An ionic bond. Now, besides the hydrogen bond, ionic bond is probably the weakest one out there. Although probably it is the weakest one out there. It occurs between metals and nonmetals. And all of these right here, all the ones I'm kind of pretending to color in, are metals, this whole thing. Columns 1 through 12, 1 through 13 are all metals, every single one of them. And when you get to carbon, well, boron's technically not, but anyways, column 14 is some of them are, 15, 16, 17. The non-metals are over here. They're kind of tucked away in this corner, the upper right-hand corner of here. Your chart actually has them. You can see where it says metal, non-metal. You see this little here, this little letter in the corner. It tells you what it is, and then also what state it comes in. So as a result of these different metal to non-metal reactions, we get what we call oxidation numbers. And oxidation numbers are the +2s and -2s that you see here on the top. So just as a reminder, like let's say lithium here as an example. Lithium has 1 valence electron, but it wants 8. So it's going to get rid of that 1 valence electron. Now electrons carry a negative charge. So when you get rid of negativity in your life, you are more positive, right? Well, it's getting rid of exactly 1 electron. So it's going to be +1, +1. Same thing with calcium here. Calcium has 2 valence electrons. It wants 8. It's going to get rid of those 2. Those 2 are negative electrons. And so when you get rid of negativity, you're positive. Now here's a little tip for you if you don't want to remember all of that. If it's a metal, it's got a positive oxidation number. It's easy. If it's metal, it has positive oxidation. The only exception would be column 14, carbon and silicon, non-metals, and this is a metalloid. but they have minuses. Anyways, if it's a non-metal, so tucked up in this corner right here, it has a negative oxidation number. Well, let's talk about negatives because I feel like that confuses some people. So let's say we got nitrogen. We have nitrogen here, and it is let's see, it invited 8 friends to its party. 5 of them showed up. That's not bad. It only needs 3 more friends to be happy and to go to cool kid status. Well, 3 electrons are going to come join this kid's party. Now, electrons carry a negative charge. So 3 negative people entered your party. Your party's going to have a negative 3 charge. Same thing with oxygen here. Invited 8 friends to a party. 6 showed up. Only needed 2 more. Those 2 more people are negative people, and they come into your party, and they're overall negative. Now, this become more important as we learn to bond things together very shortly. But I just want to go back to my list here. Let's see. Oh yes, Lewis dot. So off the same thing here, I'm going to use 2 pieces of paper to do this. So we didn't get a chance to practice it because we're not in school, but Lewis dot. Lewis dot is super easy. If I asked you to give me the Lewis dot structure of the following, hopefully you know how to do that. But let's do them together. So Lewis dot is just placing the the proper number of valence electrons around each one. So in this case, what was the first one? Carbon, right? So carbon's the first one. We go over to carbon. Carbon is in column 14, therefore it has 4 electrons. Well, guess what, guys? You just draw 1, 2, 3, 4 dots for carbon. For oxygen, oxygen is in column 16. There's 6. So if you haven't guessed already, we're going to do 1, 2, 3, 4, 5, 6 dots. Fluorine, column 17, 7 valence electrons. We draw the chemical symbol, 1, 2, 3, 4, 5, 6, 7. And finally, we get to neon. Neon's right here. Neon, we're going to draw the chemical symbol first, and we're going to draw 8 dots. 1, 2, 3, 4, 5, 6, 7, 8. So essentially, the dots represent how many valence electrons are present, and that's it. So if I asked you how many dots are on carbon, you would say 4. How many dots are on oxygen, you would say 6, and so on and so forth. So it's quite an easy way of depicting valence electrons. It's a good idea to practice, but there's no way to draw this stuff on the test. So I'm not going to expect you to draw it, but I will ask you how many dots would be around, X element and so on. So let's get into chemical bonding. So earlier we talked about beryllium and oxygen, right? I'm going to do this 2 different ways, so hopefully you'll understand it. Talked about beryllium and oxygen. So beryllium has 2 valence electrons. Oxygen has 1, 2, 3, 4, 5, 6 valence electrons. All of these electrons are going to go over here. Because remember, beryllium wants to get rid of 2 of those, and oxygen is going to take in 6. So this would yield what we call beryllium oxide. If that's too complicated for you, I have an easier method. Look at their oxidation numbers, right? Beryllium has a +2 charge, oxygen has a -2 charge. When you see +2, -2, or +3, -3, oh yeah, +3, minus, you wouldn't see minus, yeah, you would, never mind, I lied. +1, -1, when they're opposite each other, directly opposite, they cancel out, and you would just write it as them together. Let me do one that doesn't cancel out to show you what I mean. Let's say we have boron and bromine. Boron has a +3 charge. Bromine has a -1 charge. I'm going to take this 3 and I'm going to put it over here. I'm going to take this 1, put it over here. It's called the crisscross method. So I would write it as yield B, and I'm not going to write that 1 there because if I'm writing boron, I'm assuming there's at least 1 there. So I'm not going to write that 1. And I'm going to write BE 3 because that 3 transferred over here. Now, what would happen if you did write this, right? It would transfer that 1. Well, this would be what we call redundancy. We know that there's at least 1 boron there. We can see it clearly, so you don't have to write that 1. And nor do I suggest you do. Let's do another one. Let's do one that's a little more easy. Carbon and oxygen. So carbon's got a -4, oxygen has got a -2. So crisscross. C2O4. That's just crisscrossing them. And final example, sodium, chlorine. +1, -1, they're opposites. +1, -1, they're opposites. They cancel out, and you got yourself sodium chloride. Hopefully that makes sense. So use the crisscross method. If this Lewis dot doesn't make any sense, which it should, but I recommend just using the crisscross method. And if you're wondering where I'm getting these pluses and minuses and all that from, make sure to refer back to your periodic table. I'm referring to these up here. And I wrote these there. You didn't write them there. I wrote them there. All right. Now, actually, you know what? I wanted to talk about the differences between these bonds. Beryllium and oxygen here, beryllium oxide, this would be considered ionic. Why? Because beryllium is a metal, oxygen is a non-metal. Metal, non-metal. Therefore, it's ionic. Down here, carbon and oxygen would be considered covalent because both of them are non-metals. Both of them are non-metals. Now, conversely, and I don't know how to do this. I mean, I guess I could probably figure it out, but if we had 2 metals together, which this would never exist, at least like this. This would be copper and sodium. These are 2 metals. We would call this a metallic bond, but I don't think I even have it on the test. It's just one of those things that we learn. So anyways, metal, non-metal, ionic, 2 non-metals, covalent. All right, that's all you need to know for right now. We'll get into hydrogen bonds very shortly. But right now, I'm going to talk about your old favorite pal, the mole. Now you have to know how much a mole contains, right? 6.02 times 10 to the 23rd. There's that scientific notation again, right? That means that I have to move this decimal over to the right 23 times in order for this. Now this is a lot here. Remember, if this was money, if you had this much money in your bank account, you would have to spend $1 million every second from the moment you're born to the moment you die at the ripe old age of 100 years old, and you would still have 99% of your wealth left over. That's how big this number is. So you would live quite lavishly, needless to say. Okay, so besides that, what does it mean? Well, the mole is just a counting unit. That's all this is how many particles are in something. Right? You know, when you go to the grocery store, you see a dozen eggs and you know that there's 12. That's exactly what this is. When I say a mole of water, I mean this much water. When I say a mole of carbon, I mean this much carbon. When I say a mole of nitrogen, I mean this much nitrogen. That's just a counting unit. That's all it is. So what do we use it for besides a counting unit, of course? We have some various things we can do with it. So if I want to know what 2 moles of, let's say, carbon look like, all I have to do is multiply. So you would do 2 times 6.02 times 10 to the 23rd, and you get your answer. Now, if you're wondering, oh, how in the world do I do that? It's a large number. Well, it's a big number, but you can use a calculator. Now, on your test, you cannot use your phone, so don't try it. But there will be a calculator provided to you on the exam. So don't use your phone. If the proctor catches you, it's going to flag you for cheating, and I will need to give a 0. But if you have a scientific calculator like this, or even one that's a little more simpler, you're welcome to use that if you're comfortable. But if you use your phone, can't stress this enough, I will have to give you a 0 for the exam. Okay, but how do you do this? Well, we're going to take this 2, multiply it, 6.02 times 10, caret symbol, 23rd. A caret symbol is just the to the symbol right there. So what does this mean? Well, 1.204, that capital E right here, that means times 10 to the 24th power. So when you see capital E, that means times 10 to the, and then the number comes after is the exponent. Okay. Now, what if I wanted to know something different, like half a mole? All right, half a mole. Well, I do the same thing. I put in 0.5 times 6.02 times 10 to the 23rd power, and I get 3.01 times 10 to the 23rd power. Which, if you think about it, that makes sense, right? Because half of 6 is 3. Sorry, half of 6 is 3, and half of 2 is 1. So that makes sense that that would be half a mole. So in your calculators, I'll show this a little more clearly. When you want to put in a mole, you put in 6.02 first, then times, and then 10. And then this little symbol right here will always mean to the, and then 23rd would be that. And I always press equals just to make sure. But that's what a mole looks like in a calculator. Now, some more examples we'll be dealing with a concept we know as molar mass. And this is a lot easier than dealing with this, I'll tell you that right now. So molar mass is just the addition of the masses of your elements. So if I asked you for the molar mass of CO2, it's really easy. What you do is you go on your periodic table and you find, okay, carbon's got a mass of 12. So carbon's got a mass of 12. Oxygen's got a mass of, I would round that up to 16. Oxygen 16. Okay. Now, if you just added them like that and you got yourself 28, you'd be wrong. Because this 2 applies directly to the oxygen, which means that there are 2 oxygens, which would mean there's actually 32 in terms of mass. So if you're doing 12 plus 32, that's 4, and that's 4. So your answer would be 44 grams. Okay. And same thing with a different one, right? If we do, I want the molar mass of just sulfur. I'm looking at sulfur right now. Sulfur is 32. That's the molar mass of sulfur, grams. It's really simple. Just look at the chart and you'll get your answer. Now, I know what some of you were thinking probably, right? Is he going to have grams to grams, moles to grams, things like that? And the answer is no. I decided not to, only because there was so much stuff to put on here that I just couldn't squeeze it in rightfully so. But this stuff will be on here, going from two moles, half a mole. That stuff will be on there, and you'll be able to calculate it no problem. But given that you won't have a scientific calculator, at least all of you won't, didn't feel comfortable using gram to gram, mole to gram, or moles to moles, and so on. So you're free. You don't have to do that part. So I am going to move on to the next portion here. So the next portion is solubility. Pardon my writing here. The solubility is the ability for substances to be dissolved at a given temperature. So let's say, this is just water right here, right? Let's say I have water molecules floating around, and then all of a sudden I add in some table salt. Well, somehow the water molecules need to incorporate themselves with the sodium chloride, or the other way around, actually. Well, how do they do that? Well, on a bigger scale, we'll kind of, we'll zoom into this. We have oxygen and two hydrogens, right? This is water, what we're looking at here. Because the oxygen is the bigger atom, it's going to get more of the electrons, and therefore it's going to be negative. Hydrogens are smaller, therefore it's going to be positive. We know water as a polar molecule. Now, sodium chloride is very similar. Sodium has a positive charge, while chlorine has a negative charge. Well, opposites attract. So sodium is going to hook up with oxygen down here. Chlorine is going to hook up with the hydrogen up here. In other words, these two are going to split up because they found someone more attractive, frankly. So that means this sodium chloride will dissolve in water. And the more you heat it up, the more sodium can fit in there, but I'll talk about that a little later. So because water is polar, it is able to do this. Now, water is considered the universal solvent, and a solvent is something that can dissolve solutes. And in this example, sodium is the solute. Right? It's the solute. The water will always be the solvent. So in other words, the solute is the thing being dissolved or torn apart in this case, and water is the solvent, the thing doing the tearing, if you will. Now, yes, you will be expected to do these solubility curves. I'm just looking at it right now. Yeah. So solubility curves, are not complicated. I'm going to get a new paper. They're not complicated at all, right? So I'm going to draw a similar one on here. So on the bottom, you're going to have temperature. On the side, you're going to have grams of a solute. So let's just pretend here, we're going to start at 0. I'm going to say this is 10, 20, 30, 40, 50, and then we'll end it at 60. And this is also 10, 20, 30, 40, and we'll end it at 50. Okay, so we'll just put sodium around here kind of flat line, sodium chloride, I mean. So this whole line represents NaCl and what happens over time in temperature. So just by looking at it, not doing any math, you can probably figure out for yourself, as the temperature increases, the solubility of sodium stays about the same. But if I asked you, what is this, how much of whatever, how much water do you need for X amount of sodium? So what you would do is, you would go to the temperature first, you would go up to sodium, so you got to the line, and then you hang a left, and then let's say that's 42 or 41. On the exam, it's not fill in the blank, it is multiple choice, and I do make it obvious. So if you know how to do this, it'd be no problem. Now, if I asked you what's the solubility, or I'm sorry, how many grams of sodium will fit at 60 degrees? You just find 60, like I gave you. And you go up till you hit the line, and then make a left, and it'll be about the same, just by looking at it. Well, let's introduce another line here. Let's introduce something that goes like this. So this is, I don't know, sodium nitrate. Now, I want to know how many grams it's going to take, how many grams of sodium nitrate will dissolve at 10 degrees Celsius. So at 10 degrees, I go 1, 2, 3, 4, all the way up here, and then I hang a left, and I'm right there, and that's about 11 or so. I want to know how many grams of sodium nitrate will dissolve at 50 degrees. I go up from 50, pass right through the name, get to the line, and then make a left. And it's exactly 30 about. I think my line is a little skewed there. Like I said, your line will, I mean, yours will be much better, you know, in terms of what it'll look like. So moral of the story is, if I give you a temperature, you start at the temperature, you go up to the line corresponding with the name that I give you, hang a left, and you got your answer. Now, a question that might come up, excuse me, I might ask you about the temperature itself. I say, I have 30 grams of sodium nitrate. I have 30 grams of sodium nitrate. At what temperature could I dissolve it and it would be saturated? And you would just do the same thing, but start with the grams this time, work your way over to the line, and then go down to the temperature. You would say 50. So as another practice example, I might say, okay, I have 20 grams of sodium nitrate, and I want to know at what temperature can I dissolve that. You go over here to the line, you go down, and your answer would be 40. So you can work backwards like that. That's how you do solubility curves. There are a few of them on the tests. So make sure you become familiar with it. And let's see. Just going to tell you, I'm not going to be able to go over it because I'm running short on time. Know your gas laws. Know how temperature, pressure, and volume affect each other. Because it's 2 or 3 questions. Know your ideal gas law as well. And now we're going to get into material that we just covered on Monday, but we're going to cover it again. So we're going to cover pH really quick. So pH goes from 0 to 14. 0 is really acidic. 14 is very basic. The more hydrogen you have, the more acidic you are. The less hydrogen you have, the more basic you are. Bases, instead of having hydrogen, have hydroxide. That's what they have instead. So the more hydroxide you have, the more basic you are. And it works both ways. So just working with hydrogen, the more hydrogen, the more acidic. The less hydrogen, the more basic. The more hydroxide, the more basic. The less hydroxide, the more acidic. So try to get that in your head. So the more, if you work with these proportionally, it should be easy. So if I were to ask you a question, a pH of 4, does it have more hydrogen or hydroxide? It should be easy, right? Because so on this side, it's acidic. So if it's acidic, it has more hydrogen, but it also has less of hydroxide. So your answer would be, it has more hydrogen ions, less hydroxide ions. Now, more importantly, dealing with these two, when you combine them, your result is always going to be water, always. Because you have a hydrogen here, hydrogen there, that's H2, and then you have the O at the end. So it's always going to make water. And water is a neutral substance. Neutral is a 7 on the pH scale. So just to review really quick, the more acidic you are, the more hydrogen atoms or ions you have. The more basic you are, the more hydroxide atoms you have. The more acidic you are, the less hydroxide you have. The more basic you have, the less hydrogen you have. Make sure to repeat that over and over again. Okay, final thing, nuclear chemistry. Should I get another? Yeah, I should get another. Final thing is nuclear chemistry. So the first thing I'm going to start with is isotopes and notation. So remember, an isotope is same number of protons, but different number of neutrons. Okay? This doesn't say no different. This is neutrons are different. So when you change the number of neutrons, you have an isotope, essentially. And notation would be like this. So if I asked you for a stable isotope of carbon, let's just say it's carbon, you would look on your chart, find carbon, and you're going to see that it has a mass of 12 and an atomic number of 6. So the first thing you do in nuclear notation is you write the symbol down. And in the upper left, you're going to write the mass. And on the bottom, you're going to write the atomic number. So this would be nuclear notation for a stable isotope. And how do we know it's stable? Well, it's really simple, actually. If it's stable, then it most likely occurs naturally. Now, those of you who dig into the textbook or to the material deeply will know that all of these guys down here, for the most part, are unstable isotopes. But I'm not really going to ask you guys about these. I'm going to ask you guys about rows 1 through 4, mainly. So all you do to figure out stable isotopes, you look at it, and you just write down the mass and the proton number. Same thing over here. You just look at the mass, look at the proton number. You're done. I'm not going to ask you guys about these. I'm not going to ask whether they're stable or not, because the answer is probably they're not stable. So again, when you write down this in nuclear notation, mass number on top, atomic number on the bottom, which leads me to the different types of nuclear decay. So first off, let me go back to my Zoom here. So first off, we have alpha decay, which alpha decay is essentially just a helium atom. And I'll write that over here, alpha. Alpha decay is just a helium atom. And what you do is you subtract the top and the bottom. So 12 minus 4 is 8. 6 minus 2, sorry for the different sizes here, is 4. Now, what element has this become? Well, this is the proton number. So I'm going to go down here. 4, where's 4? Right there. 4 is beryllium. So I have beryllium. Now, the other thing to know about alpha is that it's harmless and it can be stopped by a piece of paper like this one. Beta is a little more harmful, although it's, in small doses, it's okay. But beta looks like this. That's what a beta decay looks like. It's got a 0 on the top and -1 on the bottom. So 12 minus 0 is 12. Hopefully that wasn't a big surprise to you. But in this case, it's a -1. When you subtract the negative, it's a positive, right? So we're actually adding this. So we're going to add 1. 6 plus 1 is 7. So only in beta decay do you add the bottom number here. And we're going to look on our chart. Beta decay, let's see, we started at carbon, it's got a 7, so we're at nitrogen now. So that's our new element. Beta decay is a little more harmful than alpha. It can be stopped by like tinfoil, but this last one is the deadliest. We call this gamma decay. Starting with the same element. This Y is the really, it's supposed to be gamma, but you get what it is. All right. So 12 minus 0 is 12. And 6 minus 0 is 6. So it doesn't change. But this is the most harmful out of all of them. This is the most harmful to humans, animals, plants, you name it. Gamma decay is, or gamma radiation rather, is very, very harmful. And it'll burn a hole right through you in a matter of a few seconds here. And this is pure energy. This is not electrons or helium atoms or whatever. This is pure energy that's being released. So let me just make sure I've answered all my own questions. Oh, duh, I forgot about half-life. One thing to know, just really quick, I saw the question passed me by there. We didn't have a whole lot of chance to talk about it, but hopefully by next week you review the PowerPoint. The element that is essential to all life is carbon, if you didn't know that already. I'm just pointing it out because we didn't have a whole lot of time to discuss it. But let's do half-life. So half-life is an element's ability to reduce its mass by half over a specified period of time. So let's take uranium, 232 and 92, all right? That's uranium. Its half-life happens every, we use an example, but let me do a different example. Let's say 5,000 years. So uranium, every 5,000 years will reduce its mass by half. Not this mass, but a different type of mass. And on the test, you will be given the mass. You don't have to guess anything. So let's say I start off with a mass of 500 grams of uranium, which is a lot. So that means in 5,000 years, I will have 250. Well, how did I get that? Well, I just took 500 and divided it by 2, right? Because that's half of 500 is divided by 2. In 10,000 years, I would have 125 grams. And in 15,000 years, you would divide this by half. And what would that be out of curiosity? So you would go into 125 divided by 2, oops, 2, and you get 62.5. Oh, that makes sense. Okay, 62.5. So in 15,000 years, I'll have 62.5 grams left over. So here's some example questions, example problems to figure out. We've kind of already done the math, so I'm gonna start with a different gram. So we'll separate this here. Still using uranium. But you know what? Actually, I'd use carbon-13. I'm gonna use carbon-13, and it decays. Oof, I forget how many years. Anyways, we'll just say it takes 10 days. That's not true at all, but 10 days. We'll just guess. It takes 10 days for carbon-13 to reduce by half. It's its half-life. Okay. How many days will it take to go from 1,000 grams to 250. You can pause the video and find out for yourself if you'd like. But here we go. So we had 10 days here. So in 10 days, we're going to go down to 500 because 1,000 divided by 2 is 500. In 20 days, we're going to go down to 250, and that's our answer. So it takes 20 days for carbon 13 to go from 1,000 grams to 250 grams. So if you didn't get how I did that, all I did was I just kind of did what I did up here. All right, so in 1 half-life, I'll be down to 500. In 2 half-lives, I'll be down to 250. Let's see. Another example might be this. Starting off with, we'll separate this again, sorry. Starting off with carbon again, it's got a 10-day half-life. I want to know how much, if we started off with 1,000 grams, how much would be left after 30 days? So sometimes in questions you're going to be given, they say, all right, in 30 days, how much of this will be left? Well, every 10 days, you reduce it by half. So 10 days, you get 500. 20 days, 250. 30 days, 125. So your answer would be 125 grams. Now, I like to work it out like this. There is a specific formula you can use, but I like to work it out like this, and I don't ask any really difficult questions. I think I ask 1 or 2 of the most about half-life. But that is the final thing on here. So I hope that helped, and I hope you're able to take this and do what you wish with it. If you have any questions, let me know. Since our exam is on Monday, I won't be able to respond over the weekend too much. But obviously on Monday, if you have any questions, bring them into class. We'll talk about them. Obviously, I have a very brief lecture to do on Monday anyway. So anyways, thank you guys for joining me. And as I mentioned, if you have any questions, let me know. If not, good luck. And I'll see you in class. Bye-bye.